Picture this. You're standing right in the middle of a brutal, unforgiving desert summer. The sun is just absolutely beating down on you. The air is incredibly thick, and there is not a single modern appliance in sight. No humming motors, no spinning fan blades, literally zero electricity. You'd think you'd be sweltering, right? Well, in today's explainer, we're looking at a 220-year-old palace in Jaipur that completely defies everything you might assume about staying cool. We're talking about the Hawa Mahal. It's this breathtaking architectural masterpiece, but more than that, it's a genuine mystery of ancient engineering. It's actually a meticulously designed machine that totally rivals modern cooling tech, and get this, it was all designed centuries before anyone even dreamed of plugging into a wall. Okay, let's dive into this, because the core contrast here is just staggering. We are talking about 45 degrees Celsius desert heat. For perspective, that is over 113 degrees Fahrenheit of blistering, oppressive warmth. And they battled it with literally zero AC units. I mean, it sounds like an impossible premise, doesn't it? How on earth can an interior environment stay naturally ice cold in extreme, honestly dangerous conditions without any modern cooling mechanisms whatsoever? Well, the secret is all in the crazy physics baked directly into the very walls of the structure itself. So let's get right into the mechanics. Section 1. The primary engine, or the Venturi effect.
To understand how they pulled this off, we really have to look at the hardware catching that desert wind, and it comes down to a highly specific number, 953. When you look at the Hawa Mahal's massive, iconic pink facade, you aren't just looking at a flat wall. You're looking at a highly complex system made of exactly 953 tiny, intricately carved stone casements, which are known as jorokas. And these aren't just decorative windows, they're actually the absolute first line of defense against that relentless heat. Think of them as the intake valves for our 18th century air conditioner, meticulously arranged to capture literally as much of the prevailing wind as possible.
And this is exactly where the brilliant fluid dynamics come into play. When that hot desert wind slams into the massive wall of the palace, it doesn't just bounce off. Instead, it's forcefully channeled right through the super narrow stone latticework of those 953 jorokas. This triggers what physicists call the Venturi effect. Basically, when you take a huge volume of air and you forcefully squeeze it through a much narrower space, that air is forced to speed up. As the velocity shoots up, the pressure drops rapidly. And that sudden drop in pressure, it cools the air almost instantly. So the building is essentially taking a hot, sluggish breeze, accelerating it and transforming it into a rapid, icy draft before it even crosses the threshold into the interior rooms. It's a total game changer.
And this brilliantly illustrates the whole sequence. Let's just walk through it step by step. Step 1. That brutal hot wind hits the massive exterior wall. Step 2. Since it has nowhere else to go, it is forced tightly through that narrow, intricate stone latticework. Step 3. The bottleneck forces the air to speed up dramatically. And finally, step 4. The resulting pressure drop cools the air instantly. So, it's this rapid-fire sequence of airflow that actively refrigerates the breeze. But, as you probably know, getting cold air inside is only half the battle of air conditioning. You have to wonder, what happens to the heat that's already trapped inside the building? Let's move to section 2 and see how this builds. We're calling this the exhaust system, or the chimney effect. You see, you can pump as much cold air into a room as you want, but if you don't have a reliable way to push the hot air out, the whole system just fails. The interior corridors inside this towering facade are surprisingly very shallow. We're talking only a few feet deep in many places, and they all back up against this large open rear courtyard. Now, this wasn't just some quirky stylistic choice for the royal inhabitants. These extreme shallow physical dimensions are entirely deliberate, and they're absolutely crucial for the next phase of fluid dynamics to actually function properly.
Because of that shallow depth and the open courtyard, the architecture perfectly leverages something called the stack effect. When the icy breeze from the Venturi effect enters those shallow corridors, it hits the people inside. It absorbs their human body heat along with any ambient heat radiating from the stone. Now, we all know the basic science here. Warm air rises. As this breeze absorbs the heat, it warms up, instantly rises up through the shallow structure and escapes freely right out into the open courtyard. It acts exactly like a continuous, natural exhaust fan. The building is literally inhaling cold air through the front and exhaling hot body heat out the back, constantly refreshing the whole interior atmosphere.
Which brings us to section 3, a thermodynamic marvel, focusing on the evaporative boost.
So the crucial point is that a massive stone lattice and a natural exhaust system are insanely impressive, but the architects in 1799 didn't just stop there. By layering multiple scientific principles on top of each other, they really perfected this machine.
They utilized thick sandstone for thermal insulation, which kept the baking sun from radiating heat directly through the walls. On top of that, they integrated historic water channels and fountain remnants all throughout the structure. When that rapid, Venturi-cooled air blew over these water features, it added an element of evaporative cooling. It works the exact same way sweat cools our skin. And finally, they incorporated deep, shaded overhangs just to protect the windows from direct sunlight. When you compound all of these elements together, the pressure drops, the exhaust system, the insulation, and the water evaporation, you get a true, absolute 18th century thermodynamic marvel. Which brings us to our final, somewhat provocative thought. Who needs electricity when you have brilliant fluid dynamics? The Hawa Mahal is just this stunning reminder that true innovation isn't always about circuits or power grids. Sometimes, actually a lot of times, it's about a masterful, deep understanding of the natural world. It really leaves you wondering, doesn't it? What other brilliant architectural secrets from the past have we completely overlooked in our modern rush for mechanized convenience? Definitely keep that question in mind, and I really hope this explainer helps you see ancient engineering in a completely new, incredibly cool light.
Welcome to the Thar Desert near Jaipur, India, in the middle of a 45-degree summer. Out here, the heat is absolute. Your only priority is figuring out how to survive it. Today, we handle this extreme climate through brute force. We pump electricity into massive mechanical air conditioning units to artificially chill our spaces. But humans have been living in this region for centuries, long before the invention of the power grid or the compressor. The intuitive architectural solution is to build thick stone walls and seal off the outside world entirely. The problem is that a sealed stone box inevitably absorbs the sun's radiation, eventually turning the interior into a slow-cooking radiant oven. The alternative, opening the building wide up to catch the wind, is even worse. That just invites a direct, unbroken blast of boiling desert air straight into your living room. So you're trapped. You can't seal the building, and you can't open it. Creating a continuously cool, breathable indoor microclimate in the 1700s looks like a physical impossibility. Yet this structure exists. Constructed in 1799, the Hawa Mahal maintains a naturally ice-cold interior, and it does it without a single modern AC unit. Every single decorative window and elaborate pink curve functions as a component in a highly calibrated thermodynamic machine. To see exactly how it works, we need to track a single gust of 45-degree desert wind as it collides with this facade, and watch how the architecture physically breaks the heat apart. The process starts outside. As the hot desert wind rolls through the city, it crashes directly into the palace's massive front wall. But this wall is porous. It's covered by 953 tiny stone casements, called girokas, each featuring a dense, intricately carved latticework. When a massive volume of ambient wind hits the building, it has nowhere to go but through those microscopic openings. It hits a severe physical bottleneck. This diagram shows the Venturi effect in action. When a fluid or gas, like our desert wind, is forced to travel from a wide space into a highly constricted channel, its physical properties change. Because the same volume of air has to make it through a much smaller gap, its velocity drastically increases. The wind is physically squeezed, forcing it to speed up as it pushes through the stone lattice. And as the speed of the air spikes, its pressure drops. That rapid loss of pressure instantly strips heat away, chilling the air right at the moment it breaches the interior threshold. So before the wind has even traveled an inch inside, the front wall has acted as a giant passive compressor, converting boiling ambient air into a sudden chilled breeze. Now, that freshly cooled breeze enters the palace's shallow interior corridors. It arrives in a space protected by thermal mass. The Hawa Mahal's walls are built with exceedingly thick sandstone, an incredibly dense material that blocks the sun's radiant heat from penetrating inside. As the breeze sweeps through these shaded hallways, it historically passed over a network of interior water fountains and flowing channels. The moisture from those channels evaporated into the dry desert wind, soaking up the remaining thermal energy. That evaporative process drops the breeze's temperature even further, finalizing a perfectly insulated, breathable microclimate. Of course, a building is filled with people. As that chilled air interacts with the inhabitants inside, it naturally absorbs their radiant body heat. Physics dictates that as the air takes on this new heat, it warms up and expands, becoming lighter. This is where the specific layout of the palace comes into play. The Hawa Mahal is incredibly shallow, only a single room deep in many places, and it leads immediately out into a large open rear courtyard. This animated cross-section shows the stack effect in action. The courtyard acts as a massive chimney. Because the warmed air is less dense, it naturally rises vertically, escaping straight up and out the open top of the courtyard. As that warm air exits the top, it creates a slight vacuum at the bottom. That pressure deficit mechanically pulls more fresh air in through the front facade's tiny windows to replace it. It is a continuous, self-sustaining thermodynamic loop. The building constantly inhales cold wind and exhales human heat, running an exhaust engine entirely on physics, with zero moving parts. A 45-degree desert gust was slowed, squeezed, chilled by water, and exhausted out a chimney, all through the precise manipulation of geometry and stone. In 1799, builders utilized the physics of pressure and airflow with precision, long before the first modern HVAC system was ever drafted. Today, we spend a massive portion of our global energy grid on mechanical air conditioning, trying to fight off a rapidly warming planet with brute electrical force. Surviving modern extreme heat may depend on a return to this ancient practice, shaping the wind rather than trying to overpower it with electricity.